whatever I have discussed under secondary refining, the different stages. I think now let me talk about how, starting from primary steel making to the continuous casting, what are the in a schematic way what is actually happening. Say primary steel making is, I have again and again mentioned, is basically either BOF or EF, or it can be induction furnace as well. But normally BOF and EF, we have most of the large steel plants, they are using either BOF or EF. Some smaller plants, they are also using induction furnaces. Now what is happening? From here we are tapping liquid steel to the ladle. So this is the ladle which will be used for secondary refining. So from primary steel making furnace, BOF or EAF or induction furnace, we are tapping liquid steel in the ladle. I have mentioned we have to be careful about the slag carried over. Slag from primary furnaces should not be allowed to come during tapping. There is a possibility of slag coming towards the end of the tapping because of funnel formation, I have mentioned. So we must have a slag topper, a slag stopper, not to allow the slag from getting carried over to the ladle. Otherwise this will create problem I have mentioned, because this slag has high amount of iron oxide, some amount of manganese oxide, some amount of phosphorus oxide. This will create difficulties in subsequent secondary refining processes. So now what is going to happen? Now we are going to do, after we tap in ladle, we are going to do ladle treatment. So how, what we can do? First I have to do deoxidation. So I can use aluminum wire fitting which can do deoxidation. Some argon rinsing is necessary, I have told you. Why? Because argon can be sent in the ladle from the bottom, because this will try to enhance the flotation of the alumina type of inclusions or silica type of inclusions which are forming by deoxidation reaction. This will enhance the inclusions to float up and get absorbed by the slag. So this is important, argon starting is important during ladle treatment. Now this ladle treatment at this stage basically means, even if I do not take it to the ladle furnace or other vacuum degassing, just in the ladle itself we can do certain amount of secondary refining, like deoxidation is possible, like argon starting is possible. So inert gas purging is possible. So deoxidation and inert gas purging, these are possible in normal ladle itself without taking it into the ladle furnace or in the degasser. Okay. Now if you want still better quality of steel, we want good desulfurization, we want degassing. So what is the way out? We have to take the ladle to the ladle furnace. So what are possibles here? Additions are possible. Additions means we want to form a good quality slag here of high basicity, because CO has to be more, then only desulfurization will be possible. So additions for slag formation, as well as additions for getting alloying elements of proper quantity. That means for ferroalloy addition can be done here. We can do argon purging also here. So we can do arc heating. If it is a ladle furnace, means we can do arc heating here. So that means the temperature adjustment in whatever processes we are doing, whatever additions we are doing, there is a temperature drop. So we have to increase the temperature. So ladle furnace provides us that facility. We can increase the temperature. If you are processing the liquid steel only in the ladle, we cannot heat it. So too much of addition is also not possible. So there is some limitations in normal ladle treatments without using ladle furnace or vacuum degassing. First, desulfurization is not possible to the desirable extent, degassing obviously not possible. Too much of addition will bring down the temperature. What we can do? We can do deoxidation, we can do argon rinsing, this is possible. So oxide cleanliness we can control, but sulfur is difficult to control only at this stage. So sulfur control, that means desulfurization, is definitely possible in ladle furnace. temperature management is much better here because we can heat. Now, instead of ladle furnace we go to a vacuum degassing units, it may be RH, circulation degassing is possible, it may be VD, it may be VAD. So, what we do, again additions are possible, again arcing is possible, like if you do VAD or RH, heating is not RH, if you go to VAD then arcing is possible, argon injection is always definitely possible. So, and if we say vacuum process means we can use vacuum, whether it is VAD, VD or RH. So, instead of normal just simple ladle treatment, if you are in ladle furnace or vacuum furnace, some more secondary refining possibilities are there. So, quality level can be enhanced further. Now, next after inclusion levels have been controlled, quality we expect that the quality is enhanced, what do? We can hold the ladle, because as I have told you, this holding the ladle will help us in two ways. First, it is possible here to do calcium treatment, that means whatever calcium injection I had just talked about few minutes back. So, those calcium wire can be fed at this stage in the ladle. This wire which is present in the spool, in the form of a spool, with the help of a feeder, this wire is being pushed deep inside the ladle. So, wire injection is possible at this stage, and then if you are holding the ladle, we are allowing the inclusions to float up, whatever alumina inclusions are forming, whatever calcium oxide aluminate are forming, this holding will help us in allowing the inclusions to float up. And if you have argon facility, which is normally all the ladles have argon purging facility, this is helping the inclusions to float up. So, after this we have to go to the turn dish if you are going for continuous casting. That means, from the ladle we have to go to the turn dish. Now, we have to again do timming, that means the steel, liquid steel whatever is there in the ladle now should go into the turn dish. Now, at this stage some refractory nozzle is necessary, because whatever care we have taken in enhancing the quality of steel, in controlling the inclusions in steel, particularly oxide inclusions, what is going to happen if we do an open timming? That means the liquid stream, when it is coming out from the bottom of ladle to the turn dish, if it is open, that means it is reacting with oxygen and nitrogen in open air. So, there will be re-oxidation, there will be re-nitrogenation. That means oxygen and nitrogen liquid steel will go up, oxide inclusions will form, and we know that due to re-oxidation, these oxides which are going to form, these are basically exogenous inclusions sort of. So, they are in large in size, very harmful to the liquid quality. So, we have to be careful about this steaming. We must do this steaming with the help of some refractory shroud together with argon rinsing. So, argon passing through refractory nozzle will help the stream to be protected, will not allow the stream to get reacted with oxygen and nitrogen. So, re-oxidation and re-nitrogenation possibility of these are controlled to the extent will be much less if you tim in presence of refractory nozzle as well as oxygen rinsing, oxygen shrouding we call it. We call it shroud, refractory shroud as well as argon shroud. Now, from turn dish, finally the liquid steel is allowed to move to the continuous casting mold. So, again the liquid steel will be coming out. So, again at this stage of timming there has to be refractory shroud, which we call is sub-entry nozzle. The liquid steel is not allowed to fall just like that. There has to be a sub-entry nozzle, and there has to be some argon shrouding to protect the liquid steel, liquid stream, the stream of liquid steel from getting oxidized and re-nitrogized. So, this is the sort of sequence of activities which are essential for getting a good amount of, or rather a good quality of steel, the desired quality of steel, to control reoxidation of steel. The total oxygen control, total oxygen content in liquid steel at the final stage should not be more than 25 ppm. If you do all this, if you take all these cares, it can be further controlled to even less than 15 ppm. If you do all this, if take all these measures and do all the controls. So, for getting a good quality of steel, we have to be very careful at every stage, starting from slag, cutting out the primary slag using slag stopper, and then taking precautions or taking steps whatever necessary at every stage of secondary refining, proper deoxidation, proper argon stirring, proper heating if necessary, because in the process you see so many steps we have to pass through. The temperature might come down, we need a particular range of temperature here during casting or ingot casting, whatever it is, continuous casting or ingot casting. So, this particular temperature to get this temperature, particular temperature, managing the temperature during the whole course of its whole course of steel making stages is very important. And when the liquid steel is coming out of primary steel making, it is relatively high, but during the process of secondary steel making the temperature might come down. So, what is necessary sometimes is to use the arcing facility of ladle furnace, or even in the vacuum arc degassing we have some arcing facilities. So, some heating is possible, so temperature management is relatively better. So, the temperature of liquid steel which is coming off the primary steel need not be very high here, because in between, if the necessity is there, we can do some arcing and temperature increase, because unnecessarily we should not go to very high level of temperature in BOF or EF, because that makes the steel dirty. Some of the refining processes are affected here. Dephosphorization is not very good if the liquid steel temperature is high. So, all these controls, the erosion of refractory is high, so the steel becomes more dirty. So, temperature at the end of BOF should not be very high. It is very easy to control temperature here, because more oxygen is put here, the oxygen combining with silicon, oxygen and all on carbon and all, the temperature will go up, because autogenous reaction here, a lot of heat is generated. But unnecessarily we should not go to very high temperature. We should not go to more than 1650, 1670 temperature, because then what is going to happen is dephosphorization is not good at the BOF stage or EF stage. We may have a lot of oxide inclusion in the steel, so the iron yield is relatively less, because some iron is lost as iron oxide, and related issues we have to face. So, if we are taking the steel during secondary refining to ladle furnace or VAD, there is a possibility of temperature control by using the reheating, reheating here. Now, whatever I was telling you, this is a temperature management, how we do it in reality. So, here liquid steel temperature after BOF or EF, say it is up to this. That means maybe it is about 1630 or so. It should not be very high, as I was mentioning. If we are using LF, it should not be very high, because there is a possibility of increasing the temperature of liquid steel during subsequent LF treatment. If you are not using LF, then possibly the temperature has to be slightly more here, because we have no scope for heating in the liquid steel, except what we call it chemical heating, that is by use of aluminum. That means aluminum oxygen reaction will generate some heat. So, there is some possibility of chemical heating, but otherwise directly there is no possibility unless you use LF or VAD. That means wherever there is no possibility of reheating, temperature after BOF EF has to be slightly more, maybe 40-50 degrees centigrade more here. In the process, the extent of dephosphorization is relatively less if you have more temperature here. So now what is going to happen? We are tapping it and we are adding the alloying elements. All these will cause the temperature to come down by say about maybe 70-80 degrees centigrade here. It is coming down to maybe slightly more, and then we are starting the ladle furnace treatment. There we can increase the temperature. So what we do is we can first make all the additions because some temperature loss will be there. Then we may add some carbon for adjusting the carbon if it is necessary, or as a first step of deoxidation we can add some carbon. So in the process we can get some temperature increase, and then using arcing we can increase the temperature. So here we have mentioned some during the heating we can add some trimming additions for adjusting the alloy chemistry. We can add some fluxes because calcium oxide has to be added because the slag has to be very high in CO for good desulfurization. Then we can do wear feeding also. For deoxidation, wear feeding of aluminum is possible here. So some purging is also possible. So at this stage, or even wear feeding of calcium is done at this stage, last stage of LF, or just outside the LF. Then we are transporting the liquid steel which is in ladle to the continuous casting bay. So again there is some temperature drop, and then we are pouring the liquid steel in some tun dish. Tun dish is already preheated before the liquid steel is poured, so there is maybe a slight increase in temperature, and then of course the casting starts. There may be slight decrease during the process of casting. So at the stage of casting, the desirable temperature is somewhere here, depending on the alloy, say it is around 1550 or so. So therefore, what should be the pouring temperature from BOF or EAF? It depends on what is our desirable casting temperature. If we take the ladle through ladle furnace or VAD, then there is a possibility of heating up. Accordingly, we adjust the pouring temperature. If we do not take the ladle through LF or VAD, so that means there is no possibility of heating, then the temperature here, pouring temperature has to be slightly more, maybe around 40-50 degrees centigrade more, because there is no scope of heating. So what is important here for temperature management is depending on the final requirement of temperature. This is dependent on what? This is dependent on what is the liquidus of the particular alloy, and some superheat has to be there. So that means what should be the casting temperature? So liquidus plus superheat, say about liquidus plus 30 degrees centigrade or 40 degrees centigrade, that is the superheat. So that temperature we have to, that means when we are starting the casting, we must have that temperature in the tun dish, because during the process of casting there may be a drop of maybe 10 degrees centigrade or so. So we must ensure when you are starting the casting, the desirable temperature is there in the tun dish, the liquid steel which is there in the tun dish. So tun dish proper heating is important here. If there is no heating of liquid steel through LF, at LF or VAD, then the temperature has to be slightly more, pouring temperature from BOF or EAF, though that is not desirable. But when there is not a provision for temperature control, that means we are not using either LF or VAD, then temperature has to be slightly more here to get the desirable temperature during casting. So this is the way we maintain the desirable temperature. And then I have mentioned how by the different secondary refining processes we get the desirable quality, how we are using at every teaming stages refractory shroud and argon rinsing, or whatever is called argon shrouding, argon protection, so that there is no deoxidation. This is very important, because whatever care we are taking for making a good quality of steel in secondary refining, that should not get jeopardized at the time of teaming by reaction with oxygen and nitrogen. So reoxidation, renitrogenation are not desirable. They have to be stopped. How do we stop it? By using proper refractory shroud, by using proper argon shrouding during teaming from ladle to tun dish and again from tun dish to mold. So, this is very important. Thank you very much.